All right, let's get started. I'm decimating the class. Maybe it's the better. Okay, so today, I do hear some echo. It's good. Okay, then it's just me. Today, I want to get to two things. Hope I make it. One is that we want to show that for no matter what the policy is, we're in a finite MDP, it has a policy, we take its value function, then the value function can be written in this form. It can be written as the expected value if you start at state S and follow policy pi of, and then usually we just write the return here, but now I'm going to write the discounted sum of mean rewards or expected immediate rewards at the states and actions that are chosen. So this is not the definition. So this is a proposition that we are working hard to show. It's a little step. So we were in this finite MDP, recall? All right. And so this is a transition kernel. And this R function here is derived from the transition kernel the following way. It's a function from state action pairs to reals. And for every state action pair, it gives the expected reward. If you take action A in state S and you transition according to that transition cutoff. So what is this? This is the sum over possible values of rewards, possible next states of the reward times the probability of seeing this reward under this transition. So this is the first proposition. The second one is the Bellman equation for pi. We want to show that okay, so here I'm missing for all S and pi and whatnot. You just imagine that that's there. I'm going to do the same for all pi and S and MDP and whatnot. V pi S, you shouldn't be this sloppy, but I'm in a rush. So V pi S is equal to, oh, and we're just going to do this for memoryless policies. Aha, okay. So pi is a memoryless policy. So what does that mean? Pi is essentially a map from states to probability distributions over actions. All right. First line. Fix pi memoryless policy. You have a Bellman equation for non-memoryless policies. Somewhat more complicated to write. Maybe it's a homework. Maybe one day you derive it for yourself. Who knows? But today, let's just take a memoryless policy. Then you take a state, and the value of this policy is equal to some beautiful formula. Sum of all actions, the probability that that policy is taking that action in a given state that we are starting from, times the reward plus gamma times, and then another sum over the next states. And there you take the probability that you reach the next state, given that you start at a state and you take action A, and there you just take the value that this value function returns at the next state. So this part is the expected value according to this value function that you're going to see if you start from state S, take action A, you make a transition to a random state, you take the expected value, and you multiply it with gamma, and you have to do this for all the actions, and the actions are weighted by their probabilities. And this is not enough, because this is just the future value. We also have to add up the current value, the value for transitioning immediately from state S using action A. This is also called the immediate reward function, this guy here. All right. And here, there is a new symbol again, the little p, that only has 3 arguments. We have all these variations. So that's also derived from the transition kernel. So there's little p at S prime, given as A, is just summing away the reward component of the transition kernel. So this is exactly the probability of transitioning to state S prime and not caring about what reward you receive, given that you were in state S and you use their action A. Okay? But these must be very, very familiar, because the book was also explaining these things. Questions? All good? All right. All right, so it's proposition 1, proposition 2. Let's get on to showing the first result. And then I think I really want to get to one more thing. If I don't get to it, I write up some notes, and then I will share the notes. It will be there. That is this other function, the action value function, Q pi, at SA. And we need a definition for it. Because if you recall, in the book, there is a definition which is given with conditional expectations. And as we have discussed, with the definition, you can easily run into trouble. So we have to work on giving it a definition that actually works. You can imagine how that is going to go. It goes the same way as what definition we cooked up for the value function. So we first have to define a probability measure over the sample space that holds all these beautiful random variables that we have. That is suitable for the definition. So you just do that. That will be the definition. And then that will give you the definition. And we just need this because it's on the worksheet too. And I mean, we just want to have everything well defined. So this whole week, how was the time spent here? I mean, it's kind of ridiculous that we're spending so much time on this. But I don't know. I just feel that if we don't define these things very carefully, rushing things a little bit too much, then later on, we might slip at any time because like our definitions and foundations are shaky. So I'd rather spend a little bit more time, and we're not going to get to Bellman optimality equations this week. We'll discuss those next week. We'll have time. We'll catch up later on. There will be not such a big rush. I think that the denseness of the material is like very quickly evaporating because you will build up the mathematical tools, and once you have those, then it will be much easier to deal with the rest. So it's kind of like at the beginning, this is tough because it's like 100 different definitions, and then, okay, you just need to connect everything up. Okay, so first statement. So what was the definition that we had? So we have to prove that proposition. We start with definitions because that's what we have. The definition of the value function was that you start with constructing this probability measure. That is the expectation that corresponds to that. That depends on an initial distribution, your policy of choice, and then you just sum up all the future rewards. Okay? So the only difference between what you see here in the definition and what you see there is that here in this definition, you have this random variable RT plus 1, and there it is swapped to R of ST and AT. That's the only thing that's happening. And we just want to argue that you can do that. It should make sense. It's like we are taking expectations, and like whether you first take the expectation over the random reward given where you are and what action you chose, should give you the same thing as taking the expectation altogether for the random return. But I'm doing this formally so that you can also, like catch up with this formal reasoning. And if I ask you to solve some problems, you can do the same thing, right? Because I can't prove everything. So sometimes you have to get into these things and then show these things for yourself and convince yourselves that they do work. Okay, so the first thing that we tried to do is to argue the last time that you can move the sum outside of the expectation. And what I ended up telling you that this is not so simple. And we had to call a theorem. It's called Lebesgue's dominated convergence theorem. So what this theorem does is that it allows you to argue of interchanging expectations and sequences of random variables. So if you have a sequence of functions from your sample space to the reals, which are random variables, so for every n, you have these guys, and we will connect these momentarily to those. And you also know that for every little value of omega, so for every omega in this sample space, Fn omega converges to some value. The limiting value is going to be denoted by F omega. So there exists a function that's from omega to the reals, such that there is this pointwise convergence that holds. This is called pointwise convergence. Because for every point, the function values are converging to some value. Okay? And there is one more condition, that there is some function, let's call it g, which is also from the sample space to R, such that all these functions f, are upper bounded by g. I mean, like I could define this non-negative valued, but whatever. So this inequality here, if you're comparing two functions, like what does it mean to that one function is less than equal to the other function? What's your guess? What should it mean? When I say, what's your guess, you can be wrong, right? Because I'm not expecting you to know the answer, but you can guess. It's like, how do we compare two functions? So you can imagine the functions like, here's the real line, maybe it's over there, one function goes like that, the other function goes like that. When would you say that, okay, like this first function that I waved in the air is smaller than the other function?
Depends on the norm you're talking about, I guess.
There's no norm. Yeah, so imagine that this is your little omega. I don't need to wave, right? I have a board. And this is your function fn. If I have to draw some function which is above fn, what should that mean? It could mean many things, like maybe at one value, that function is higher than fn at one value of omega. That could mean that. It could mean, I don't know, something else, like that the integral of one function is bigger than the integral of the other function, or whatever. But it's not. No, it's meaning something else. What's your guess? In what sense? This is just like functions not used for, they're used for the sake of being functions and like nothing else. Yeah.
Take an upper bound on f for ln or fn.
Right. Yeah. Like, okay, so there is a function, and for every value, that means that you have some value. And there is some other function, let's call it g. And we would say that g is above fn, or this notation, g is greater than equal to fn, if it holds that for whatever value you take of omega of the domain, the value that g takes is at least as large as the value that fn takes. Here's the thing. Especially if you have a finite domain, there is no difference between vectors and functions. Because what is kind of a vector? A vector is a list of values. Okay, so maybe the only difference is that if you have a list, there is an ordering of the values. And when we're talking about functions, we don't really care about the ordering of the values. We care about what value we take at some point. If you have finitely many points, though, then you can order them arbitrarily and always get out of a function a vector. Okay? So why am I saying this? Because maybe you have heard about that you can compare vectors. And if you're comparing vectors, that usually also means this. And also, why am I telling you this? It's because a lot of times it's very useful to see functions as vectors. You can add vectors. What does it mean? You're adding them point by point, like component by component. That means the same thing as point by point with functions. And so we do that with the functions as well. Actually, it is very sneaky because we already use this a lot. It's very, very sneaky. Here, I'm writing a sum over what? What are these? These are functions from omega. So, yeah, it's just probability theory. Or when you're dealing with probabilities, you're dealing with random variables, then you're summing up functions all the time. And you can also compare functions like you would compare vectors, the same thing. All right, so here in this notation, there is one more thing, which is that I wrote absolute values. So let me expand this. This just means that that's the definition of it, that for every little omega, the absolute value of fn omega is less than equal to the absolute value of g of omega, right? So pointwise, the absolute value, in absolute value, g dominates fn. Okay. And that's a standard notation as well, that you just put absolute values next to a function, and that just means pointwise absolute value. You would not think for a second, if I put an absolute value here, you would think right away that that's what's happening. I mean, under the hood, that's what's happening. All right. Okay. All right. So Lebesgue dominated. This is the setup for it. And what does the theorem say? The theorem says that if all of these things hold and one more thing holds, the expected value of whatever distribution you had some probability distribution over omega. Then the expected value of Fn converges to, there is one more condition, but let me just say that this is what it's going to say to the limiting function, the expected value of the limiting function, provided, so assuming that the expected value of the absolute value of G is well defined, it's finite. In this case, it just means because it's non-negative value. So this means that it's finite. All right. So that's Lebesgue dominated convergence theorem. How are we going to use it? Fn is going to be the partial sum from 0 to n of the return. Okay.
Sorry.
Yeah.
So I thought like in the Lebesgue dominant convergence theorem, you don't need absolute value on G basically. Like
if G is no negative value, then you're right. But like I define it as a real valued function, and then I mean you don't actually, because it's just like if you I didn't write the absolute value here, this would be forcing it to be non-negative value anyway. So it's like, but it doesn't matter. Sometimes it's just easier to write a G and later take the absolute value. So it's good both ways. It somehow looks better to my eyes here, this way. And since they are completely equivalent, it's fine. But it's a legit question. All right. So this is Fn. What is F? Right, so it's the limit of this. We want to argue that the limit of this exists, and whatever that limit is, we want to use that as F. And so we had already a notation, and we had a discussion the last time about that this converges pointwise because of our finiteness assumption. Geometric series converges. You can upper bound all the values of RT plus 1 with the maximum value of the possible rewards. And then you can use the convergence of geometric series to argue that this converges to something, some limit. And syntactical sugar, we call that limit, we just denote it by like that the sum goes from 0 to infinity. So that's just like a notational, thing that we use. That really just means the limit of this sequence. So this converges, and we discussed that, to F, which we can define to the infinite sum from 0 to infinity of the discounted return. So this is just reiterating what we already knew. What to use as G? This other function.
I mean, since gamma is less than 1 anyway, I guess we're assuming that, right? Like.
Oh yeah, absolutely, yeah. It's like not on the board, but yeah, we would be in deep trouble if that was not the case.
Sure, then I can just bound it by RT plus 1 because gamma of t times RT plus 1 is always going to be less than RT plus 1 since, like, I guess my G will be just sigma of n of RT plus 1, right? Like, because each term is.
What RT plus 1?
Sorry, like the summation of from t to 0 to n of RT plus 1, because that is my G basically. I'm
okay. So you take away the gamma.
Exactly, because it's always bounded is less than 1. So
right. So that's true. That would be an upper bound on F if it existed. But maybe that infinite sum doesn't exist, right? So you can just like take a single state, you're looping back, you always receive a reward of 1, you sum up infinitely many ones, and that diverges. And so that doesn't work.
I see the sum.
We want a G that is well defined, which is upper bounding all the FNs. Yeah. We just said that everything is finite here. S, A, R, and R is also finite. So there is a maximum value. So we can, since R is finite, I can introduce something like R max, which is going to be the maximum absolute value for the rewards that are possible. And then you can use many G. Actually, this would be fine as G as well. You just have to show that this expectation is verified. And we argued for that before. So you could use that as G, but it's kind of the same thing to say that I can define for G of omega to be the same infinite sum, except that I swap RT plus 1 with R max. And then I can pull out R max, and the infinite sum converges. It gives you 1 over 1 minus gamma. So G would be just R max divided by 1 minus gamma. Okay. The expected value of this exists? Does it? Why? It's just a constant, right? So the expected value of constant is a constant. That's how kind of like expected values are set up, right? It's a discrete random variable, which just happens to be a constant. And the expected value of that discrete variable just happens to be the same constant, right? OK. So every condition is satisfied. So Lebesgue tells us that taking the expectation on the partial sums and then taking the limit is going to give you the expectation of the infinite sum. Good, because we had the expectation of the infinite sum, and we just wanted to move the sum out, and we just wanted to say, OK, lim n goes to infinity. T goes from 0 to n. And then here I have, OK, going slowly, just moving the expectation inside. And I'm, all right. So here I'm dropping these indices, but they are there. Just imagine that they are there. OK, I don't want to write that much, and it's too much clutter. So for the sake of the proof, in the context of this proof, that expectation means this expectation. All right. All right, just moving this in, and then syntactical sugar again. Mathematicians like abbreviations, which are kind of intuitive. So this is just the same thing as writing sum this up from 0 to infinity. OK? It's just like recalling what you have learned a while ago in calculus. All right. Next property of expectations. When expectation is well defined, you can move out from the expectation a constant. And gamma to the power of t plus 1, or t, is a constant. So that can come out. So we get this. All right, that was hard work. We had to learn about Lebesgue's theorem. Man. All right, this statement is going to be gone, and I will squeeze everything. All right, so we can deal with the individual terms there. And remember that we just wanted to swap this RT plus 1 to this value that the little r function takes at STAT. All right, so let's work on that. And then once you do that, you would reverse the argument, because once you swapped, okay, so maybe I just finished the proof, sort of, with a question mark here, because this step is not proved yet. And then I just use the other board to prove that. Sometimes it's good to kind of jump ahead, but then remind yourself that, okay, like this is questionable here. But so this remains to be seen. But if I was able to show that this expected value is the same as this expected value here that I'm writing, so you can swap the random rewards expected value at time step t to the expected value of what the immediate reward function gives you at that corresponding state action pair, then you would have this. And then you can move this back in. And then you can move back the infinite sum inside the same argument. Again, you would call the Beck's-dominated convergence theorem. And you can argue that you can move back the infinite sum inside. So then you get that this is the same as the expected value of this. All right. And then you say, QED, great, we're done. Except that that one step remains. But at least we see the light at the end of the tunnel, right? What did we get ourselves into? Eh? All right. So we need to calculate this expectation. That's what, well, we want to show that this is equal to this. So somehow bring in the state action pair, STAT, that happens at time t. So how do we do this? Well, there are many ways. One way is to expand the expectation using conditional expectations. That's our friend a lot of times. So if you have a complete set of events, then the total law of conditional expectations or whatnot, like chapter 3 of this book that I'm trying to market to you, tells you that you condition on all possible events. You take the probabilities of the corresponding events, take the corresponding conditional expectations, sum everything up. This weighted sum gives you the expectation. So that's the total law of conditional expectations or whatever. It's one of those things that you have in probability theory. And so here, I can take as possible conditioning events all the events that correspond to this state at time step t, and this action at time step t corresponding to a particular value. They are mutually exclusive events because the state can only be one thing at a time, and the action can only be one thing at a time. So they're mutually exclusive. And they're complete as well, because I'm going to list all possible states and actions. All right, so I can use this law. So I'm summing over all states and all actions. And then I need to take the probability that the state is something, little s. The action is something else, little a. So this is a complete sequence of events that this corresponds to. And then conditioning on, so then the conditional expectation of the random reward, given that the state was this, and the action is this, right? OK. So now we have to go back to our definitions of what P was. There is no other way. We defined what P was. So P was defined using trajectories of length t and what probabilities you get for those trajectories. So those probabilities we know exactly. So from those probabilities, we need to derive a probability for just this state being S and this action being A. So there we have to use other laws that connect different probabilities. So this other law is again a total law. So it's always just like the total law of probability, total law of expectations, total law of condition, just total law. So everything is all that you need. I don't know. Right, so there's going to be a claim that the probability that ST is equal to S. Wait, no, I'm making big mistake here. Don't do that. Right, so there could be a claim, but don't bother. So this would be the mistake of calculating something that you don't need to calculate. All right. So let's focus on the other term because that's where the action is. We want to somehow get rid of RT plus 1. So let's just focus on this term. Okay. I almost got myself into a deep hole. Okay. So let's calculate this. It's just like, yeah, like in chess, you have to think a little bit ahead of like, okay, what happens if I calculate this? Is anything good going to come out of that? Not really. So let's do the other thing. So it's like priorities. So the priority is to get rid of RT plus 1. So let's work on this term. We definitely have to do something about this. So let's not worry about that term. If we need to worry about it, we come back to it. All right. So what's this condition expectation? So the condition expectation is just like an expectation just with conditional probabilities. Conditional probability is only defined if the event has positive probability. So for every SA such that this probability here, that ST is S and AT is A, is positive, for this, the conditional probability of seeing whatever is well defined. Condition on this corresponding event. So this conditional probability is well defined. So what is this? An expectation is the sum of possible values. We are discrete here, very discrete. The whole class is discrete. Sum of possible values. So this is replaced by some possible value, R prime. Could be R2, but like just be consistent. Times the probability that you're going to see that value. But in this case, it has to be conditional probability. All right. That doesn't belong. Yeah. All right. That's good. So we still have RT plus 1. Trying to get rid of this guy. So let's work on this term. So what do we do about that? We have to take the pill. We have to write out what that probability is. So what is that probability? Well, it's a conditional probability. How is a conditional probability of, I don't know, the probability of even condition like on B, on even A condition on B? What's that? It's PA given B is PA and B divided by PB, right? So just using the definition. And here we are really lucky because we can divide by this guy. because it's not 0, because we assume that it's not 0, because we don't need this probability when things are 0, actually. Okay, and here we have to take the probability that this happens and this happens. So just write them. So in probability theory, you have this funny thing that this thing here really means all the little omegas that RT plus 1 omega is equal to, oh, by the way, this is R prime, R prime. So that's a subset of omega. And it's like everything is a subset of omega, but you never write it because it would be so cumbersome to write it, but it's under the hood. That's what's happening. And the other strange thing is that you have these sets. You want to take intersection of them. And OK, you're not writing the curly braces. If you don't write the curly braces, then taking intersection is kind of like, oh, what do? You use a comma. So the comma is used to denote that you're taking intersections of these corresponding sets.
So why is the expected value of RT plus 1 given ST equals S and AT equals A? Does the giving even matter because you're going for a next before the current state doesn't matter?
What is the question? What is the why part of it?
The question is the expected value of RT plus 1 given ST equals S and AT equals A equal to the expected value of RT plus 1?
No.
No? Okay.
Because you can think about it that if you start from some state, after some steps, t, you're at some random state somewhere. So you have some probability of being in this state, in that state, and so on and so forth. And at every such state, you will receive some reward. Maybe not even random, but like some reward. In this state, you receive 1. In that state, you receive 2. But OK, if I say I want a condition on being in this state, there I receive a reward of 1 with probability 1. In the other one, maybe I receive a 2, and you have to kind of mix them together. So the difference between the unconditioned expected reward and the conditional expected reward is that here I'm kind of tying down the state. It's like anchored to that state and action. All right, good question. It's like, yeah, it's like kind of this mixing is happening. All right. OK, so just syntax sugar, this comma just means intersections and so forth. So this is why I can just write this very, very short formula. All right. But under the hood, I'm taking the intersections of all those sets. I think probability theory is like coding in Prolog or something. Have you learned Prolog? It's like you write some code and you never know what happens. It's like very, very high level. But actually, you need to know what happens, right? So it's like we're just like practicing that. OK. All right. So we're not going to do anything about this because, OK, if you look back, you're also multiplying with this. So it's like that's going to happily cancel. And that was my mistake. That earlier I wanted to write an expression for this, but they would just cancel. So you don't need that. But we need something for this. So what's that? What's in the numerator? So the probability that RT plus 1 is equal to R prime, and ST is equal to S, and AT is equal to A. So no moment of truth. We have to say what this probability is. There is no further way. And how do we do that? We're going to use the law of total probability. We're just going to invent histories that end with this sequence. You start with some state, initial state, you take an action, you see a next reward, you see a next state until you encounter this state. Then you take this action, and then you see this reward, and then maybe you see a next state. And we know what the probability of that full history is because that was the definition we used. And then we sum away everything in that full history except these guys. So that's the law of total probability. All right. So this is equal to And it's just going to be an ugly, long expression. So you sum over S naught, initial state, initial, I don't know, action. And then you have R1, that's a reward. And then the next state, that's a state, and so on and so forth. And you go up to, well, we're not going to use ST or AT because for that we already reserved S and A. And we're not going to use RT plus 1, but everything before that. So the last thing that we're going to have is RT minus 1, which is in R. And we also want to have a next state because that's how things were defined. So we're going to have an ST plus 1 in S. And so dot, 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 and capital RT minus 1 is equal to RT minus 1. And, sorry, capital RT, actually. That's what I want, RT. And then, because it always comes with, you take an action. Well, OK, wait. We have actions. OK, this was AT minus 1. Yeah, you have like the indexing starts with S naught, A naught, and then a switch comes. When there is an index switch, then you write the reward. OK, so this is the first variable that has an index of t. And then here you have just S and A, no indices, and RT plus 1 is equal to R prime, and ST plus 1 is equal to ST plus 1. All right. So this is just the law of total probability. We define a set of mutually exclusive events that are complete in the sense that they generate a full event space, the full sample space. If you take their union, this is what happened here. And then a probability can be written as that, like probability of an event is the event intersected with elements of that event set and summed up. So it's basically, OK, I do have a picture for this. I do have lots of these pictures, and we have a board. Take advantage of that. You have omega here. There are all these events, and you're wondering about the probability of this guy. What you do is that you slice up the full event space in some way, partition it, and then you say, well, whatever was the probability of this event is the probability of the sum of its intersect of the parts of the partition that I put on the full space. So the probability of this, and the probability of that, and the probability of that, and the probability of that. So that's the total law of probability. It's like some simple thing that follows from the axioms. OK, that's what you use here. Why do you use it? Because we know what this probability is. So again, this is going to be the sum over the same things. I'm not going to write it. But this probability, the definition was on the board. It's going to be this Dirac function at S naught times the probability of taking that action A naught at state S naught, and then the probability of seeing this reward and next state, given that you took that action in that state, and so on and so forth. And then here, OK. So let's write dot, dot, dot up to you take this probability. Actually, I have to write the probability of this. So the probability of seeing RT and S, given that you were at ST minus 1, you took action AT minus 1. And then there is the probability that you're taking this action given the history up to that point. So S naught, A naught, RT, and S. And then there is the probability that you're going to see this reward and this next state. So that's I prime and ST plus 1, given that you were at state S and you took action A. And this whole thing is summed up over everything but SA and R prime. Okay? So what is this? If you write it out, it's going to be the sum over ST plus 1 in S of P R prime ST plus 1 given SA. All the other terms are going to go away. How do you argue about that? You can argue by first, I guess, summing from backwards would be the best. So you just take this off, like you're going to keep this. And then you start to sum over, OK, you can't really sum over this. Wait, what is that? What? Huh? Last two terms? What? There was no sum over A. Yeah, like the last two terms remain. That's right. And then you sum over the RT here. And then from that, you just get this probability. I mean, OK. It's over time, so I will give you this in the notes.